Welcome to EDU World Space.
Okay, so our question is asking us about Lewis structures, molecular geometry, and hybridization. So before we jump into how to draw those structures, what we need to kind of understand is that Lewis structures are written as a way to show how electrons are distributed within a molecule. Molecular geometry is a way of describing the shape of molecules once they're formed. So once we distribute the electrons using a Lewis structure, we then want to determine the shape that the elements make around a central atom. And then the last thing is hybridization. So hybridization deals with what type of orbitals are overlapping or interacting to form specific bonds. So now we're going to look at our first structure, which is NH3, or also known as ammonia. So ammonia, if we look at our periodic table, the nitrogen in ammonia has a valence number of 5. And hydrogen has a valence electron number of 1. So when we add these together, we get 8. We total all of these up. So this is the total number of electrons that we need to distribute. Let's go on and total up for arsenic and chloride. And so we're going to come back and do our structures for each. So for arsenic, it has a valence number of 5. Chlorine or chloride has a valence number of 7. So when we total all these numbers, we get a number of 40. So we have 40 total electrons we need to distribute. For phosphorus bonded with fluorine, phosphorus has a valence number of 5, and fluorine has a valence number of 7. So 42, because 6 times 7 is 42. 42 plus 5 is going to be 47. So we have to distribute these 47 electrons. So now let's go back here. We know that nitrogen is going to be our central atom, and we're going to start forming bonds. Nitrogen is happy when it has at least 5 valence electrons. So let's make sure that nitrogen is happy. Hydrogen is happy with only 1. At max 2. So we're going to start distributing the electrons. So 1, 2, 3, 4, 5, 6. So now we've already distributed 6. So 8 minus 6 is equal to 2. We have 2 left over. So we're going to give nitrogen its lone pair. And due to the fact that nitrogen has this lone pair, we can automatically determine the molecular geometry. So the molecular geometry from this distribution is going to be trigonal pyramidal. So I'm just going to kind of write it shorthand, but trigonal pyramidal is this one. And the hybridization of it, so we see that we have a bunch of s and p orbitals overlapping. So the hybridization of this is going to be sp3. And now let's look at arsenic bonded to 5 chlorides or 5 chlorine atoms. So we've got 40 electrons. We automatically know that chlorine is happiest when it gets at least 7, but it'd be happiest at 8. Arsenic is happy at 5, but it could be happier. So let's start distributing the electrons. We're going to make a bond. Obviously, a bond is made between two electrons shared, especially in this type of covalent bonding. So we've got 1, 2, 3, 4, and then 5, 6. So this arsenic is going to bond with this chloride, and then 7, 8, 9, 10. So we have 10 electrons we've already used to distribute to our central atom, and we've got 30 left over. So now we're going to distribute the 30 left over to the individual chlorine atoms until we make sure that each one has almost a full octet or close to it. So let's start with this atom. Let's add 1, 2, 3, 4. Actually, let's just start by adding 2 electrons back to each of these chlorine atoms. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we just distributed 10. We got 20 left over. So let's distribute again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we use 10 again. And we have 10 more to distribute. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now all the chlorines have a full octet of 8, and arsenic is happy. It has 10 electrons. And so from this, we can look and see that this structure is actually going to form a trigonal bipyramidal molecular structure. So I'm going to just shorten the word, put trigonal or trig bipyramidal. And if we look on our periodic table, we'll see that arsenic is on the, I believe it's on the 4th row. So it automatically has the D structures or the D orbital, which means that it can form as many bonds as possible because it has this D orbital, which can normally fit more electrons than normal. So because of this, its hybridization is going to be sp3 And remember that I mentioned it has a D orbital. So because it forms so many extra bonds and can share more electrons than the normal range is 8. That's when most elements are happiest. But because it has this D orbital, it can accept more electrons and share more. And so we're going to have an sp3d hybridization. For this phosphorus bonded to 6 fluorines, now let's count this. So we already counted that we have a total of 47 electrons we've got to distribute. So now we're going to just make a bond between each of these fluorides with the phosphorus. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've already distributed 12 electrons to the central atom, and now we have 35 electrons left over. So now we're going to distribute those electrons to our fluorine atoms. So remember that fluorine is very similar to chlorine. They're in the same group. They require a 7 electron valence shell, but they are happiest with 8 electrons. So let's see if we can make each of these atoms reach their full octet level. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So far we've used 12, and we have 23 left over now. So now let's try to distribute again. So we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now we're going to subtract 12, and we have 11 left over. So now let's try to distribute our last 11. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this fluoride or fluorine is only actually going to have it's going to have one less electron than all the others. And these structures could even have resonance because there's going to be some instability. And so in order to create stability, there will possibly be some resonance because this fluorine is actually missing an electron. Therefore, again, there's going to be some instability, and that's when resonant structures occur in order to promote stability within the molecule. So now looking at this structure, we see that whenever we have 6 atoms or ligands that are symmetrically arranged around a central atom, like we see here, so phosphorus is our central atom and fluorine are all of the ligands or atoms that are bonded to this phosphorus, we see that there's 6. So this is going to be in octahedral molecular geometry. And the hybridization is going to be sp3d. And the reason it's sp3d is because, again, you see that we have multiple bonds. So instead of just phosphorus being happy with 8, it's actually going to have, it's bonded to 6 atoms, which is equivalent to 12 electrons. And it's due to the d orbital being present. So any elements that are on the 3rd row of the periodic table and below can form these d orbitals or have d orbitals, which can accept more electrons than normal and therefore give elements like phosphorus the chance to bond with more than just 4 elements bonded to it. And therefore we get a hybridization like sp3d2 for this molecule. The question also is asking about why nitrogen or NF5 and nitrogen bonded to the 6 chlorides or chlorines, why those are not formed. So the reason why those are not formed, remember we've been talking about the d orbital. So with nitrogen, if you look at where it's located on the periodic table, it's actually in the 2nd row. Remember that I said that any elements that are on the 3rd row and below can do or can perform the d orbital properties or functions where they can hold more electrons. Unfortunately, because nitrogen is only on the 2nd row, it does not have a d orbital like some of the other elements that are in its same group. So arsenic is in the same group as nitrogen. However, it's also in or row 4. Therefore, it has the ability to hold more electrons and form more bonds, and that's what gives it its property. But nitrogen can only form the normal 3 to 4 bonds because it lacks the d orbital.